Hey guys, this is Austin.
This is Richard, and here's our final presentation on the Busy Beaver problem.
So, a brief overview on what we're going to present. We're going to start with an introduction on computability and undecidability, and then talk about Busy Beaver and what it is, followed by Busy Beaver functions, and then the relevance to our course. So, some background. This Busy Beaver problem was introduced by a Hungarian mathematician, Tibor Rado, in his 1962 paper on non-computable functions. The purpose was to teach beginners about Turing machines and non-computable functions, so he created the Busy Beaver problem as a simple way to explore these concepts. And then here's some introduction about computability and decidability. A problem is said to be computable if there exists an algorithm or a Turing machine that solves it in a finite amount of time. Essentially means that it halts. And as for decidability, a language is decidable if some Turing machine decides it. And a Turing machine deciding means it halts on all inputs and always outputs the correct answer depending on whether the input is a valid solution to the problem. Some examples of undecidable problems are Hilbert's 10th problem and halting problem, both of which we've talked about in class. So the Busy Beaver problem. The goal is to design a halting Turing machine with a binary alphabet that writes the most ones on an infinite tape given a certain number of states. And the rules for this Turing machine are as follows. The Turing machine must only have n states in addition to the halting state, and the tape must begin with all zeros. An n-state Busy Beaver would be a Turing machine that attains the highest number of ones among all other possibilities of n-state Turing machines. And each state contains three possible values: the overprint, shift, and call. Overprint just tells you what value to write on the tape. Shift tells you to move left or right. And call moves you to the next state. So this is an example of a one-state Busy Beaver that doesn't halt. We have the three values here. And from earlier, we know that the tape begins with zeros only. So when the Turing machine sees a zero, it prints a 1, shifts left, then calls A. And this is a self loop, so it never ends. And this tape is also animated. And you can see that it endlessly prints ones and shifts left. Because this Turing machine doesn't halt, it doesn't satisfy the requirements of the Busy Beaver problem and is accounted for a score. So if we think more in depth about a one-state Busy Beaver, there are 64 possible Turing machines. For each of the two inputs, there are 3 binary values. So each input can result in 2 to the power of 3 or 8 actions. And with 2 inputs, there are 8 to the power of 2 or 64 possible Turing machines. But if you think about it, there are only 4 possible cases. The case where the Turing machine prints infinite ones to the left, infinite ones to the right, a single one to the left and halts, or a single one to the right and halts. And we can determine these from the examples that the max number of ones that a one-state Busy Beaver can print on the tape is 1. And here we have a 2-state Busy Beaver, now that we tackle the 1-state. And this is known as one of the optimal solutions for a 2-state Busy Beaver, which results in 4 ones being printed on the tape. So why is this problem called the Busy Beaver? The idea behind this metaphor are that beavers are busy working to perform the operations specified by the rules of the Turing machine. They are working as fast as they can. However, how long will they be able to keep working before they halt? This is where we talk about uncomputability and undecidability of the Busy Beaver problem. The number of possible Turing machine configurations is infinite, and it is not possible to check all of these configurations to determine the maximum number of ones that can be produced. Hence, we're following up with a proof.
Now, we shall prove that the Busy Beaver problem is uncomputable and undecidable. Let sigma of k be a function mapping from the natural numbers to the natural numbers such that sigma of k equals n if for all Turing machines with k states that hold an input epsilon, n is the maximum number of ones left on the tape when started with epsilon as input. Now, suppose we had a method of computing sigma of k. Then we could decide ATM as follows. For some m x, let m prime be the 2-tape machine that on the empty string as input simulates m on input x on one tape, while appending 1 to the other tape each time it simulates a step of m. Then let k prime be the number of states of m prime, and let n equal sigma of k. Run m prime on epsilon for at least n steps. If m prime hasn't yet halted, m loops forever on x. We have thus created the decider for ATM. However, ATM is undecidable. Therefore, sigma of k is undecidable and therefore uncomputable. Now let's go over some functions relating to the Busy Beaver problem. For some Turing machine m, define S of m equals the number of shifts m takes before halting, sigma of m as the number of ones on the tape when m halts, n of n as the number of possible n-card Turing machines, where n of n equals 4 times lowercase n plus 4 to the power of 2n. We'll explain this function a bit later in the following slides. S of n, which is also called the maximum shift function, is the max of S of m, where m is some n-card Turing machine. Sigma of n equals the max of some lowercase sigma of m, where m is some n-card Turing machine. This is our Busy Beaver function. This is the function that counts how many ones are left over on the machine when it is halted. Now let's try some calculations for a 2-card Busy Beaver. Now, if you might remember 1 card, the solution for 1 card is pretty trivial. The only valid configuration is setting exactly 1, 1, either to the left or to the right. It's trivially obvious to the casual observer that looping forever to the left or right results in a never halting Turing machine, and we can disregard that for the Busy Beaver problem. For 2 card, n of n equals 4 times 2 plus 4 to the power of 2 times 4, which calculates out to 20,736. Wow, that is a big number. Remember, we're just at 2 card. And for all of these 20,736 Turing machines, we have to go through each Turing machine configuration and calculate them by hand. We can also prune some of them out. For example, if we read the cards on the Turing machine and we know that they never halt, we can eliminate these because they are not relevant for the Busy Beaver problem. Now, we calculated out that the maximum number of ones you can achieve with the 2-card Busy Beaver is 4, and the maximum number of shifts you can achieve is 6. So how many Turing machines can we have with 3 cards then? Yes, you read that right. At just 3 cards, Busy Beaver can end up with 1.7 times 10 to the 7 possible Turing machine configurations. We'll see how fast the Busy Beaver explodes on this slide. At 1, we have 64 configurations, and at 2, we have 20,736. As stated before, at 3 cards, we have 1.7 times 10 to the 7, which then grows on to 2.6 times 10 to the 7 at n equals 4, 6.3 times 10 to the 13 at n equals 5, and 2.3 times 10 to the 17 at n equals 6. That's just for n of n. Now, you might be wondering what happens to sigma of n? Well, sigma of n equals 1 for n equals 1. That grows to 4, then 6, then 13, then maybe 4098. I'll explain that later. And then 3.5 times 10 to the 18,267. That is a mind-blowing number. Now, you might be wondering what that question mark means. The question mark means that we actually have not found a concrete answer for that value of n. So as explained before, we actually have to run through a large amount of the Turing machine configurations. And at n equals 5, we have 6.3 times 10 to the 13 configurations that we need to run through. Some of these can be pruned out, obviously, but at large numbers of n, it's not obvious if Turing machines are looping. For example, at 1, anyone can figure out that, oh, this machine is just printing out ones infinitely to the right. But at large values of n, the periodicity of the loops gets very large, and it becomes non-trivial. Now, why is this important? The Busy Beaver problem, as we stated before, is uncomputable. In other words, no algorithm can determine the solution to this problem in a finite amount of time. This means that the Busy Beaver function grows faster than any computable function. For example, the famous Ackermann function grows slower than the Busy Beaver problem because the Busy Beaver problem is uncomputable and the Ackermann function is a computable function. That's all we have for today's lecture, and thank you for listening.
Thank you.